So thank you very much for the kind introduction and for having me here. So I want to discuss a question which has reached me several times in the last year. So I'm an academic research fellow at LUT-University of Technology. So I'm paid by the Research Council of Finland. But I'm also a regular lecturer at the African Institute for Mathematical Sciences. And what you see there already is that a lot of students, they ask, when you come there, they ask, so why should I actually do applied mathematics? Because now there's all the data science. And if I study something traditional like applied mathematics, I will, at least in Africa, not find a job. And I want to argue that no matter whether you're in Finland or in Africa or somewhere in the US, I mean, the question is, do we need applied mathematicians? I'm an applied mathematician, so I'm not going to say that they are redundant, but both of them will be needed in a certain sense. So I try to make the point that it is actually worth studying applied mathematics and understanding something about artificial intelligence and neural networks and stuff like that. So maybe if we want to understand whether we need applied mathematicians, so we should have a look at what an applied mathematician usually does. And I just took my profile here. And it's kind of symptomatic for an applied mathematician, but of course it will differ from person to person. What is kind of in common for all of them is that there's three main branches, yeah? So one of them I branded models and applications. So that's basically somebody comes to us with a research question, and that's the kind of questions that we try to answer. So we need to understand at least something about those questions. And then at the bottom there is kind of two dimensions. One of them is usually that we need to implement our models that we do into some computers to make them alive. So that's usually done in some software. So if you are an applied mathematician, then usually you somehow have the skill to program to a certain extent, yeah, or do some high performance computing even. And what you need to do is you need to use some mathematics tools. Yeah, I call them numerical schemes because they are usually what is used to kind of turn a PDE into a software program, or like a model that somebody can understand into a software program. There's something in between, which is the mathematical layer. And you also need to understand that. And then most of us applied mathematicians, we stay along a lot of the time on this numerical scheme side, making our methods faster, making them better, making them, I don't know, understandable, things like that. But our main topic should always be to answer some real-world questions. Yeah? So that's always what everything revolves around. And I want to kind of make the point that in my case, there's four main research fields. That's elasticity. I call it phase fields, porous media, and shallow water. And what is the good thing if you're an applied mathematician? Those are very, very general topics. Yeah? So you can apply them in many things. So elasticity, for example, I applied in astrophysics, but we also will see something like an electric engine where we are interested whether its elastic behavior is correct. So if you understand elastic object, then of course to an applied mathematician, it only matters to a certain extent what kind of an object that is. Yeah? Then there's phase fields and porous media, which kind of, in my case, belong together. So porous media is you look at something like soil, which is a natural porous medium. Everybody can imagine that there's kind of two ingredients to soil, a porous matrix, which consists of some solid and some void. Yeah, and might be fluids or gases that kind of travel through this porous medium. And then, for example, we worked with Shell, and they are always interested in kind of getting the most out of soil when it comes to oil. Yeah, so you want to optimize that if you drill a hole and you want to get oil out, then kind of getting as much oil out without damaging the environment too much is one application. But then again, you can use the very same tools to kind of ask the question, how should farmers treat their soil to grow plants very efficiently? Or soil should have many, many other aspects as well. Soil should be very stable when you want to build roads on it or bridges. Soil should kind of keep the water very much in it when you're in a very dry region. So if you're somewhere in Africa, you don't want the water to go away very fast because the plants need the water and it doesn't rain that often, or in some regions at least. While when you are in very flood-prone areas, you want to treat your soil such that it kind of absorbs a lot of water and the water goes away to kind of diminish the influence that floods have. And the last one is shallow water that I want to emphasize here. And shallow water is also, it sounds like you're only kind of thinking about very, very small lakes. But in fact, what you're thinking about are oceans, for example. Yeah, so shallow just means that the horizontal extent is much, much larger than the vertical extent of the water body. So oceans are typical bodies, water bodies of that type. But then weirdly, you can use the very same models or similar models to predict the weather and do things like that. So you have, as an applied mathematician, you have several fields of applications, yeah, and you can tackle many applications or true applications with those. So I want to look at soil science as a first kind of model application. Yeah? In this context, we were interested in what the soil kind of, into these very small parts of the soil. This right thing is, so on the left picture, you see a piece of soil. And on the right picture, you see a microaggregate. So you zoom into the soil. And if you get to the scale where you have like a few hundred microns, then you see objects like the right thing. And clearly, like, you want to kind of influence the soil on the very huge scale, so like the left picture. But if you can kind of manipulate the soil, then you can kind of do that by kind of putting some ingredients on the soil. You kind of can manipulate the right picture only. And then what soil scientists try to do is they wonder, what can I do to manipulate this very small object such that soil has these properties that I described? So for example, that the soil becomes very, very stable. Or for example, such that the soil has the property that it kind of absorbs a lot of water. Or for the property that you can grow plants there every year, and those plants grow very efficiently. So those are questions that you want to answer. And the problem, of course, is there's a difference in scale. Yeah? So what you understand, or what you try to understand, is on the very small scale. You have to transfer that to the very big scale. But the problem begins even earlier. So what I can do is I can create these small objects in a very controlled environment, but I cannot see how they grow. Because every time I take these objects out of the controlled environment and I measure them, usually I have to destroy them. So if I want to measure, for example, the stability of such a microaggregate in the right picture, well, I can do that only once, because I will kind of, naively speaking, put as much pressure on it till it cracks. So if you want to kind of see what processes drive nature towards building very, very stable microns, then that's not an efficient process. And another thing that I want to highlight here is kind of doing these experiments is very, very expensive. So if you think of Shell, yeah, and they want to kind of get as much oil out of soil as possible, then what they need is some probes from soil, which are very, very deep in this hole where the oil is. So it's very, very expensive to get to these soil pieces. And if you destroy them, you don't have many of them. So you want to kind of investigate them as cleverly as possible and use as few of them as you can, and use as much of expert knowledge or of applied mathematicians, of something that you can control, to get as much information as possible. That is the idea. So how does an applied mathematician then work? Well, usually some expert who knows much more about the topic than I do than applied mathematicians do, comes to an applied mathematician that has a very, very detailed question. In this context, it could be, okay, how can I treat soil such that my aggregates grow very, very large? That's also a popular question, because a last aspect that soil should always satisfy, and that's very much underestimated, is the fact that if you have a healthy soil, and then the first 7 centimeters of the soil, if you take a handful of that soil, then there's more microorganisms in that soil than live on planet Earth. And those microorganisms, they have the ability to bind carbon in the soil. So you want to keep the soil healthy in that sense, to kind of diminish the impact of global warming. So you want to kind of bounce CO2 from the atmosphere in the soil. So it's not only the plants that bounce CO2 and grass and the things that we usually have in mind, but soil itself is also a key player when it comes to binding CO2. And I mean, everybody knows that in Siberia, in this soil, there's a lot of CO2 bound, and when it unfreezes, then there will be a problem for climate. But the same kind of also happens in every country in the world almost. So you could have the question, how do I grow those microaggregates very large, which is a healthy environment for these microorganisms that live in soil? Yeah, so basically these experts, they come to applied mathematicians, and they have a very precise description of the problem, and they kind of have an idea on how those microaggregates kind of grow. Yeah, because they have made experiments, they have seen a lot of those microaggregates, they know how robust they are. But they, for example, want to know how those microaggregates evolve. And then the problem usually is that those experts and the applied mathematicians, they speak different languages. Yeah, when I talk, I speak in terms of equations and in terms of very, very abstract physical principles that maybe they use the same words, but they mean something completely different in their world. So it's a first step is kind of understanding each other, and it's most often the hardest and also the most crucial step, because if that step goes wrong, then the whole machinery kind of starts. And well, the machinery kind of ends. You show your results to that person who asked the question, and the person says, well, all of that is garbage because actually you have missed the most important point. Then you start again over and over. So that's something that you do, and then there's two steps that applied mathematicians do, and that kind of correspond these two level bottom points that we had in the first picture. The first one is to translate these phenomena into equations, yeah, and there comes something like elasticity that you have, or heat transport, or things like those that you kind of want to do, or in other kind of models. So sometimes, usually the language in which mathematicians talk is equations, but sometimes it's not equations, and sometimes other models are more appropriate. So you try to select an appropriate model, and then you kind of try to mimic the physical behavior in terms of that model. So there's a lot of abstraction there. And then the last step is bring that model to life. Yeah? So the last step is implement that model in the computer such that you can show the outcome to the expert, and then you can, for example, switch off certain phenomena in the model, and you see what phenomena drive specific processes. So if you are interested in very big microaggregates, then you would try to kind of switch off some phenomena and see, do the microaggregates grow? And if they grow by switching off a phenomena, then you try to diminish in the real world the causes of that phenomenon. So that is kind of the idea. So how could such a model look like? Well, in the big picture for soil, there's these two levels. We say, okay, we have a microscale. There usually the models look relatively simple, hopeful, or very often. So you have some behavior on the microscale. Then there is a step which is kind of magic, where mathematics kind of kicks in, and you can kind of mathematically justify that if the microscale looks in a certain way, then on the macro scale, which is here on the bottom, then you get a certain outcome. For example, if you want the soil to kind of have water travel through very fast, then you would see that on the macro scale, yeah, so the meter scale, while the micro scale is the scale of millimeters or even smaller, so you wouldn't kind of see a huge effect there. So you have to translate that. And well, while all of that is kind of complicated and not really accessible to people who are not mathematicians, how that goes, we can still have a look at the micro scale. That's the model that we're actually interested in. So we can start out with a very, very simplistic model for the micro scale. So in this model, for example, so it's a cellular automaton model. Cellular automata, they're very prominent and very popular in the 1960s for a specific reason. They can capture a lot of different behaviors, so they can do a lot of, you can model a lot of things by them. And the second thing is that they are easily accessible, they are easily understood, usually. And in this context, you could have two phases where the brown guys here, so that would be the solid phase. You could think of sand corns or something very, very small sand corns. And the blue guys are the liquid phase, yeah? So for example, water or gas. So that's where our small microaggregate lives. Yeah? For example, here we use those to kind of mimic the formation process of microaggregates. So they had laboratory experiments where they kind of broke up microaggregates to their kind of elementary building units. Those are the small brown cubes, for example, here. And then you wonder, how do they kind of form together? And then there's two processes that kind of might be there. First process might be something dominated by charges, yeah? And that basically says, okay, you have charged surfaces. For example, yellow would be a positively charged surface, and magenta would be a negatively charged surface. And then you would kind of allow them to move in stencils of size 2. Yeah, and then you can have a look what happens. So first, for example, this guy C here would move. Yeah, so, well, evenly charged surfaces don't want to attach to each other. So if he goes to the bottom and to the right, then magenta surfaces will meet. So that's not a very favorable position. And it kind of, if it goes along the orange kind of arrows, then of course one yellow and a magenta surface will meet. So that's very electrically favorable. But the best position is kind of rotating by 90 degrees and going twice to the right end. Yeah, so it's a very, very, very simplistic model for a process that's actually relatively complicated. And then, for example, this guy D, who's uncharged, might move, and that one might just maximize the number of neighbors that it has. So that's a very, very simplistic model for mimicking something which is diffusion-driven and driven by electrical forces. And then those kind of particles kind of go together and try to form big particles. So that's what you do here. And that's the most simplistic model that you could have. And now the question is, can we get something from that model already? So let's just start with such a model. Yeah, so you think of, okay, you've broken up the aggregate into very, very many small black dots here, and they float in some water, which is here gray. And then I kind of let this model run for a long time. And what I see are those two possible outcomes as two categories. The left outcome and the right outcome. And they stem from the very same initial kind of condition, but they are significantly different. So in the left, we clearly see that there's blocky structures, which we sometimes see in soil as well. And in the right picture, we see kartals or dendritic structures, as they are called. And now you could kind of say, okay, how did I kind of make those two pictures? Well, in the left one, I switched off the electric effects. While in the right one, I kind of let the electric effects dominate. So what that tells us is if I want aggregates that are very blocky, for example, then I need to kind of form an environment where electric effects are either non-dominant or not existent, or they are not the kind of important thing. Well, if I want a dendritic environment, then I should kind of go for I should kind of treat soil such that electric effects play an important role, and that you can kind of steer by kind of changing the pH value in soil. So those are very, very simple models where you can already kind of, together with experts, you can try to learn how to build soil in a very, very, very simplistic way. And then again, so if you want to kind of build very big kind of microaggregates in soil, then you can do other experiments. Here you have like red circles, and you have like very, very small plates and needles. The circles being quartz, the needles being graphite, and the plates being illite. And then you kind of want to, for example, build as big aggregates as possible. And what mathematics can do is we can kind of try all the combinations to throw into this pot and kind of let them form and see which one gives you the biggest kind of aggregates. And what you learn then, you do a lot of evaluations, and what you roughly learn is that the biggest aggregates are formed when the electric charges kind of balance out. So if there's as many positive charges as negative charges, and it's well distributed in your tank. So those experiments are very, very expensive, and what experimentalists want to do is they want to do only the experiments that are very promising. So mathematics can at least exclude some experiments for being absolutely unreasonable to do. Then another application that we have is electric engines. Here the models become a bit more complicated. So those consist of the three bottom parts, and they are put together in a shrink-fit method to create the upper guy here. So that's the full engine, so it's induction motor rotor. And what you want this guy is you don't want to behave it like at the bottom here, so that it bends like that. So what people are wondering is, okay, there's a guy in the middle that kind of rotates all the time, and if it hits an eigenfrequency, so basically then these oscillations get stronger and stronger all the time, and finally the engine will break. So you could wonder in which rotational speeds can I run the engine safely, yeah? And that's of course an experiment that you don't want to do on a daily basis because some of the engines might break. So you want to have mathematics or which you can rely on. That's the important point, yeah? So the solution might not be perfect, but you can kind of guarantee that it's never completely off to kind of check those things. And then as an opposite thing, I'd like to discuss how the machine learning approach goes. Well, I really break it down here to a definition of machine learning that's from the last century, because, well, today there's many kind of ways to describe the very same thing. But if you boil it down to something, to a free adults, then it's basically instead of writing a program by hand and understanding the model, what you do is you have a relatively generic program and you feed it with an absurd amount of data, or sometimes not an absurd amount, but at least with a lot of data that you have collected as examples. And it learns basically from those examples the function or what input should yield which output. That is kind of the thing. So the machine learning algorithm then takes the examples and produces a program that does the job. And this program is not understandable usually, or very hard. It's at the brink of, it's the bleeding edge of research to understand those things. And because these programs consist of a lot of numbers and ways to transform those numbers. So you usually don't understand what they do. And the key idea is that now basically investing a massive amount of computational work is much cheaper than kind of using human resources, the human brain, to understand models. Yeah, and what this concept does, basically it will give you some input to output mapping. Yeah, so you could give it like an engine, and it will tell you whether it will fail or not. But first of all, you will need a lot of examples of engines that worked or failed, and you will never want to create those examples. Or you could, in theory, get mappings that tell you, okay, if I have this configuration of particles, it will give me a small macro aggregate or not. But you need a lot of experiments to have done before. So either you have done these experiments in the computer, that would be so-called physics-informed neural networks, or that's at least one of those aspects, or you do them in real world, and then everything gets really, really expensive. So there's the main kind of branch of this machine learning that does that is the so-called supervised learning. And if I rephrase it a bit, then what I want to do is I want to learn a function that maps some input values to some output values, x to y. And that's the main kind of branch of machine learning that kind of combats applied mathematics, I would say. It's used in many things, so risk assessment, image classification, spam filtering, and things like that. And what those things have in common is that there's a huge amount of data available and easily available. It's easily available to have like millions of pictures and then having a human saying it's a cat, it's a dog, it's a rose, it's a sunflower, and then make the machine learn it. But of course, if these experiments become extremely expensive, then you wouldn't want to do like thousands of those experiments. And then the main questions related to machine learning are then again, how do we actually efficiently learn or train the machine? So using as few examples as possible, while at the same time wanting to be like reliable. So we want to guarantee that the machine learning algorithm never fails drastically. And the third one is, where do we get the training data from? And my kind of conclusion would be that this is exactly where we need applied mathematicians. Because now, actually, you could see the machine learning problem as one of those problems like soil science, like having an electric engine that doesn't want to fail. You don't want the machine to fail. So actually, what traditionally is done is basically that machine learning is treated as one of those engineering tasks or science tasks that we discussed so far. And thereby, it is actually essential to be an applied mathematician to understand machine learning to a certain extent. And then I want to close with the last slide, so answering who needs whom. So basically, it's not a world of good and bad. So machine learning is a tool, and it depends whether it's a good tool or not, depends on how we use it. So basically, we can use it very much if the speed up that machine learning provides justifies possible violations of some physics, because, well, the humans they incorporate physical laws into their models. So, for example, they want to be mass conservative, or they never want to kind of gain momentum or lose momentum. So that's something that the machine learning algorithms do not understand at this moment. And if I have a sufficient amount of data that I can create or already have available, or of course, if I don't have a physically reasonable model, then I can try to use machine learning and try to get some knowledge via that. And on the other hand, machine learning needs applied mathematicians to make the learning process more efficient, to understand the machine learning and to make it explainable at best. Because if we could explain how the machine learns and what kind of concepts it exploits, then again, we would be in the game that we can learn from machine learning as we can learn from doing numerical models or applied mathematics models as we do today. And with that, I want to thank you for your attention.